Okay, welcome back. So we are delighted to introduce our next distinguished speaker, Professor Susanne Brenner, who is a Boyd Professor at Louisiana State University. Professor Brenner is widely celebrated for her influential contributions in the area of finite element method and related techniques. So she holds fellowships in both SciAm and AMS. So please join us in extending a warm welcome to Professor Brenner as she steps onto the stage.
Thank you very much for the introduction, and I want to thank the organizers for the invitation to this very interesting conference. So this is joint work with Liang Sung, Jiyu Tan, and Hongqiao Zhang. So this is the outline of my talk. First, I'll say a few words about the Monge-Ampere equation. Then I'll describe our method on convex polygonal domains and discuss extensions to convex smooth domains. And I'll end with some concluding remarks. So details can be found in these two papers. So this is the Monge-Ampere equation in 2 dimensions. This is a second-order partial differential equation that's nonlinear in the second-order derivatives. In other words, it's a fully nonlinear PDE. The linearization of the Monge-Ampere operator is given by the Frobenius inner product of the cofactor matrix of U, cofactor matrix of the Hessian of U and the Hessian of V. Therefore, the linearized Monge-Ampere operator is elliptic if and only if U is strictly convex. So we assume that F is strictly positive and look for strictly convex solutions of our Monge-Ampere equation. So let me show you 3 examples of Monge-Ampere equations. These examples can be extended to higher dimensions, but I'll only mention 2D examples here in this talk. The Monge-Ampere equation appears in the prescribed Gaussian curvature problem. So if we let sigma be the graph of a function u in 2 variables, the Gaussian curvature of a graph is given by this formula. We let omega in R2 be a bounded convex domain, and k be a positive function defined on our domain omega. The prescribed Gaussian curvature problem is to find a surface sigma passing through the boundary of omega, so that sigma is the graph of a function, and the Gaussian curvature of sigma over any point x equals k. It's illustrated by this picture. We can construct sigma, hold on. Oh, it's slow, the delay. Now it went fast, sorry. We can construct sigma as the graph of a function u by solving a Dirichlet boundary value problem for a Monge-Ampere equation. The Monge-Ampere equation also appears in the Minkowski problem. So given a positive smooth function k on a unit sphere satisfying this condition star, we want to find a convex surface sigma so that k of x is the Gaussian curvature of sigma at the point y, where the unit outer normal is x. In shortwave acoustic diffraction, the reconstruction of a convex obstacle from the far field scattered wave of a point source can be reduced to the Minkowski problem. Nierenberg proved that there's a smooth convex body unique up to translation that solves the Minkowski problem. And this was extended to arbitrary dimensions by Zhang and Yao. The idea is to find sigma by finding its support function h of x on the unit sphere. We can then recover the surface sigma by differentiating h. The support function satisfies a differential equation on the unit sphere. And if we take u to be h with x3 equals 1, then star becomes a 2-dimensional Monge-Ampere equation. There are 6 Monge-Ampere equations for the 6 functions associated with the 6 faces of the cube that bounds the unit sphere. We can find h of x by solving these 6 Monge-Ampere equations on the 6 squares to obtain solutions that are compatible on their common boundaries. The Monge-Ampere equation also appears in optimal transport. We have 2 domains, omega and omega star. And we have a mass density phi on omega and a mass density phi star on omega star. A material originally distributed in omega according to phi is to be transferred to omega star, so it's distributed according to phi star. This requires a necessary mass balance condition. An admissible mass transfer is a measurable one-to-one map S such that the mass balance condition is satisfied for every open subset E of omega star. And we'll denote the set of all admissible mass transfers by A. For a sufficiently smooth mass transfer S, we can rewrite the mass balance condition by using the change of variables formula. The optimal transport problem is to solve a minimization problem where C represents the cost of transporting a unit mass from point X to point Y, and this integral is the total cost of using the mass transfer S. In the case where the cost is the square of the Euclidean distance between X and Y, the optimal transfer S is the gradient of a convex function. The condition that S is admissible can then be expressed in terms of U. The optimal transport problem is therefore equivalent to the Monge-Ampere mapping problem, consisting of a Monge-Ampere equation together with a state constraint. Optimal transport with this particular cost function has many applications. There's a growing literature on numerical methods for the Monge-Ampere equation. There are geometric finite difference methods. There are monotone finite difference methods. There are augmented Lagrangian and least squares finite element methods. There are finite element methods based on the vanishing moment approach. There are finite element methods based on L2 projection. There are finite element methods based on a Hamilton-Jacobi-Bellman reformulation. There are two-scale methods. And there are fixed point iteration methods. Today we'll consider the Dirichlet boundary value problem of the simplest Monge-Ampere equation as a stepping stone to more complicated ones. Our method for computing smooth, strictly convex solutions is completely different from all the methods existing in the literature. It's based on the simple observation that a solution of the Monge-Ampere equation is strictly convex if and only if the Laplacian of U is greater than or equal to 0. First, let's consider the case of a convex polygonal domain. So this is the Dirichlet boundary value problem for the Monge-Ampere equation with an additional constraint that enforces the strict convexity of the solution. We assume that the function psi in the Sobolev space H2 is positive on the closure of omega, that the function phi belongs to H4, and that there exists a unique strictly convex solution U that also belongs to H4 omega. So let me point out that in the case of a strictly convex smooth solution, we can remove the third assumption, provided that psi and phi are sufficiently smooth, but it's easier to explain the ideas behind our method in the case of a convex polygonal domain. So we need to enforce this constraint, and we can do this by using an exotic finite element. which I will call the enhanced cubic Lagrange element. So here, T hat is the reference simplex in blue. T hat dagger is the larger triangle. The space of shape functions is a direct sum of the cubic polynomials and the product of the P1 polynomials and the square of the bubble functions. The degrees of freedom for this exotic element consists of the degrees of freedom for V from the standard cubic Lagrange finite element, which are represented by the dots in red in the picture, together with the values of the Laplacian of V at the vertices of the larger triangle, which are represented by these black triangles. One can show that a shape function is uniquely determined by its degrees of freedom. Of course, this is not a finite element in the classical sense, since 3 of the degrees of freedom are at nodes outside of the element domain. But we can do this because polynomials are defined on the whole plane. So here's a useful observation. If Laplacian of V is non-negative at the 3 vertices of the larger triangle, then the P1 interpolant of Laplacian V associated with the larger triangle is non-negative on the larger triangle, and therefore it's also a non-negative on our reference triangle in blue. This is how we enforce the convexity of our approximate solution. So T hat dagger is the triangle whose midpoints are the vertices of the reference simplex T hat. For a general triangle T, the corresponding triangle will be denoted by T dagger. So the enhanced cubic Lagrange element on an arbitrary triangle T is affine equivalent to the element on the reference simplex. The space of shape functions is the direct sum of the cubic polynomial and the product of the P1 polynomial and the square of the bubble function. The degrees of freedom consist of the degrees of freedom for the standard cubic Lagrange element together with the values of the trace of this matrix at the vertices of the larger triangle T dagger. So here, JT is the Jacobian of an affine map phi T that maps the reference simplex to T. Let me point out that the values of the trace of this matrix are the values of the Laplacian of the pullback of V. I'll refer to the trace of this matrix as our scaled Laplacian. So now I can define the finite element space VH. So let TH be a quasi-uniform simplicial triangulation of our convex polygonal domain omega. A function V belongs to the finite element space VH if and only if V is continuous on omega, and the restriction of V to the triangle T belongs to the enhanced space. The global degrees of freedom of a function of the finite element space are given by the global degrees of freedom of the cubic Lagrange finite element space, together with the values of the scaled Laplacian at the vertices of the larger triangle T dagger. So here's a picture of the global degrees of freedom. The red dots represent the degrees of freedom for the standard cubic Lagrange element. The black triangles represent the 3 extra degrees of freedom. Now, if I would have put these black triangles at the correct locations outside of the triangles, they would have conflicted with the red dots. And they would have conflicted with each other, and that would be really, really confusing. But since these extra degrees of freedom are not shared by the triangles, I put the notation inside the triangles. So now I can show you the discrete problem. We will find an approximate solution by solving a nonlinear least squares problem with box constraints. A finite element function belongs to the constraint set LH if and only if it's the one-dimensional cubic Lagrange interpolant of phi along the boundary. And the scaled Laplacians are non-negative at the vertices of the larger triangle. After we remove the boundary values, these are the degrees of freedom for our computation. We then define the approximate solution UH to be a minimizer of this cost function. So this is our discrete problem, where dH squared V is the piecewise defined Hessian of V. EHI denotes the set of interior edges of our triangulation, and this denotes the jump of the normal derivative of V. This last term is the least squares discretization of the Monge-Ampere equation. The third term is a penalty term that compensates for the fact that the finite element space is not in H2. The first term is a regularization term, which together with the penalty term ensures that the discrete problem has a global minimizer. Because we have a Poincare-Friedrichs inequality that implies that as the L2 norm of the finite element function goes to infinity, the cost function also goes to infinity. The second term, involving the scaled Laplacian, is a regularization term that enforces the element-wise convexity of the discrete solution. We have a priori bounds for a minimizer of our cost function. We have an interpolation operator pi h, defined by the condition that zeta and pi h zeta have identical degrees of freedom. This means that pi hu is the one-dimensional cubic Lagrange interpolant of phi along the boundary of omega. Let me point out that we can extend u to the whole plane so that pi hu is well defined on the exotic nodes outside omega, and the extended u is strictly convex in an open neighborhood of the closure of omega. This also means that for any triangle T, the scaled Laplacian of pi hu, which equals the scaled Laplacian of u, is positive at the vertices of the larger triangle. Therefore, pi hu belongs to our discrete constraint set. So this is the cost for UH, which is less than or equal to the cost of pi UH, because UH is a minimizer. And we can use our interpolation error estimates to show that every one of these four terms is bounded by h to the power 4. So we have this inequality in red, which is equivalent to these four a priori bounds. So these a priori bounds are crucial for the error analysis of the nonlinear least squares methods. They're based on the important fact that pi hu belongs to our constraint set. It then follows from an inverse estimate that we have an L infinity bound that implies that the determinant of the Hessian of UH is strictly positive. So let me now demonstrate the element-wise convexity of our minimizer UH. By construction, the scaled Laplacian of UH is non-negative at the vertices of our larger triangle T dagger. Therefore, the P1 nodal interpolant on the larger triangle is also non-negative. Consequently, it's also non-negative on our triangle T in blue. On any triangle T, we have this inequality because the norm of the Jacobian matrix is equivalent to H. We then subtract a non-negative term. We can make it more negative by taking the L infinity norm. Then we apply our interpolation error estimate to cancel one of the H's. Then we apply one of our a priori bounds. And we saw earlier that the determinant of the piecewise Hessian of UH is strictly positive. And we just saw that on each triangle, we have a lower bound for the trace. So there are two possibilities for the eigenvalues of our Hessian. They're either both positive or they're both negative. If they're both negative, then the lower bound for the Hessian, the lower bound for the trace implies that their absolute values are bounded by H. And we have a contradiction to the lower bound for the determinant that we had at the top. So we can conclude that both eigenvalues are positive, and the function UH is strictly convex on each triangle T in our triangulation. So let me sketch the a priori error analysis. By the fundamental theorem of calculus, we have this equation where AHX is defined at all the points in omega except those at the edges of our triangulation. Since U is strictly convex, we have this estimate for all vectors C and R2 and at all x in the closure of omega. At any point x that's not on any edge, we can then estimate this quadratic form. Our second integral is non-negative because UH is element-wise convex. We then apply this estimate in red and integrate. So now we have this lower bound for the quadratic form. Therefore, our equation star is related to the error analysis of discontinuous Galerkin methods for elliptic equations in non-divergence form in convex polygons. We have a stability lemma that's already in the literature in slightly different forms. So I'll just describe the ingredients behind this lemma. The first ingredient is a relation for H2 functions that vanish on the boundary of a polygonal domain. The second ingredient is an enriching operator, EH, that satisfies this estimate. The third ingredient involves techniques for proving the existence and uniqueness of strong solutions for elliptic equations in non-divergence form that satisfy the Portas condition. I don't know why there's a lag. Okay. The functions u minus phi and uh minus pi h belong to the correct spaces by the boundary value problem and the definition of our constraint set LH. Therefore, we can apply the stability lemma to these two functions. So this is the stability estimate. We then apply a triangle inequality. But these two terms in blue are the same by the fundamental theorem of calculus. So now we have this estimate. We can use a priori bounds and interpolation error estimates to show that all four of these terms are bounded by h squared. So we end up with this estimate. And consequently, we have this estimate. And from an a priori bound, we also have this result. So putting everything together, in summary, we have this theorem. And we have these estimates for the L2 norm, the H1 norm, and the L infinity norm by using the Poincaré-Friedrichs and Sobolev inequalities for piecewise H2 functions. We also have an a posteriori error analysis. Now recall UH is the minimizer of our cost function. Now since the cost function is non-convex, an optimization algorithm usually only produces an approximate stationary point UH tilde. The a priori error estimates for UH does not guarantee that UH tilde will converge to U. Now suppose that UH tilde is element-wise convex. Again, by the fundamental theorem of calculus, we have this relation where AH tilde is uniformly elliptic. And by the same arguments as in the a priori analysis, we have this estimate where the oscillation of phi is bounded by h squared. Therefore, we can use the error estimator A to h, defined by this formula, to monitor the convergence of UH tilde to U. So now let me show you some numerical results. We'll present the numerical results for two examples with known solutions. The first example satisfies all the assumptions in our theory, and the second one has a less smooth solution. Our discrete problems are solved by an active set algorithm of Hager and John. And the element-wise convexity of our approximate solutions is verified numerically. For each example, we compute the relative errors in the H norm, in the H1 norm, in the L2 norm, L infinity norm, and using our error estimator. In our first example, the domain is the unit square, and we have a very smooth exact solution. These are the relative errors, and the error estimator, and the computed times. In less than 3 seconds, we already have a very accurate approximate solution. We can see the reliability of the error estimator by comparing it with the relative error in the H norm. So let me go through this step by step. First, second, third, and the next one, and the next one. So you see they both have second order convergence. We've also tested the same problem on 4 other regular polygons, and the performance is similar. So these are the convergence histories in the H norm for the 5 regular polygons, and the L infinity norm. In the second example, we have a piecewise smooth C1 generalized solution. So we use uniform meshes in the computation, and we check the approximate solutions are element-wise strictly convex outside this disk. So here are the relative errors, the error estimator, and the computational times. In less than 8 seconds, we have a very good approximate solution. We've also tested our method on adaptive meshes generated by the error estimator using a Dirichlet marking strategy. The solution obtained by adaptive meshes performs better in the H norm and also in the L infinity norm. And we see that the adaptive mesh clearly captures our singularity. So now let's turn to smooth domains. We have the same boundary value problem on a strictly convex smooth domain. As I mentioned earlier, now we don't need to have to make artificial assumptions on the solution. The first step is to construct an isoparametric mesh. So we begin with a convex polygon omega h tilde that approximates omega. Then we put a triangulation th tilde on omega h tilde such that these 3 conditions are satisfied. We want that the vertices of omega h tilde belong to the boundary of omega. Each edge of omega h tilde is also an edge of th tilde. And each triangle in th tilde has at most 2 vertices on the boundary of omega. We can obtain the isoparametric mesh TH by modifying the triangles in TH tilde that have two vertices on the boundary of omega. First, we modify P4 and P7, represented by the solid dots, by the directional derivatives at the nodes P2 and P3 that are represented by these arrows. We then modify a triangle T tilde in TH tilde with two vertices on the boundary of omega into a triangle T with one curved edge by using a cubic polynomial map on the reference triangle that's defined in terms of the degrees of freedom of our modified cubic Lagrange element. So here's the picture. In this picture, T tilde is the straight edge triangle with vertices P1, P2, and P3. Then we use a cubic polynomial map phi t to modify T tilde into a triangle with one curved edge. So here's the definition of phi t, which is from a 1972 paper by C.R. Lay and Raviar. I won't go into the details of this, but it's important to note that P3 hat is mapped to P3, and this vector is mapped to a vector tangential to the boundary, of omega. Similarly, P2 hat is mapped to P2, and this vector is mapped to a vector tangential to the boundary of omega. So these are the key properties of the map phi t. The curved edge of our triangle T is tangential to the boundary of omega, the two vertices of a triangle that belong to the boundary, and it's a good approximation of the boundary of our domain between these 2 points. Now, there are two types of triangles in the isoparametric mesh TH. It can be a triangle in TH tilde that has at most one vertex on the boundary of omega, or it can be a triangle with one curved edge that's a modification of a triangle with two vertices on the boundary of omega. Now, the domain omega H is then the union of all the elements from the isoparametric mesh. It's a strictly convex domain if H is sufficiently small. And our discrete problem is posed on this domain. For a straight edge triangle, we use the enhanced cubic Lagrange element from before in the first part of the talk as our reference element. For a triangle with a curved edge, we use an enhanced modified cubic Lagrange element as the reference element. Everything's the same, except we change 2 degrees of freedom. So now we can define an isoparametric finite element space in the usual way. For each element T, the map phi t is an affine map if T is straight edged, and it's a cubic polynomial map if T has a curved edge. Now a function v will belong to our finite element space vh if v is continuous on omega h, and the pullback of v belongs to our enhanced space that we described earlier. The degrees of freedom of the pullback are the degrees of freedom of the enhanced cubic Lagrange element if phi t is an affine map, and their degrees of freedom of the enhanced modified cubic Lagrange element if phi t is a cubic polynomial map. Now recall, we can treat the solution u of the boundary value problem of the Monge-Ampere equation as a function that's globally H4, such that u is strictly convex in a domain of omega closure. Now for h sufficiently small, the Laplacian of the pullback of u is positive on the larger triangle T hat dagger. This is obvious if phi t is an affine map, and it's based on the approximation properties of phi t if it's a cubic polynomial map. We have an interpolation operator that's defined by the condition that the pullback of zeta and pi h zeta have identical degrees of freedom for all triangles in our triangulation. Now, by construction, the restriction of the pullback of pi h zeta on the edge of t hat corresponding to the curved edge of t is the one-dimensional cubic Hermite interpolant of the pullback of zeta. Now, since the curved edge of t is tangential to the boundary of omega at its two vertices on the boundary, the restriction of pi h zeta to the boundary of omega h is determined by the restriction of zeta to the boundary of omega. So now we can define our constraint set LH. Since pi h phi is determined by phi, which equals u on the boundary, we have this relation on the boundary of omega h. The key observation is that pi hu belongs to our constraint set LH. So here's our discrete problem, which is to find a minimizer of this cost function. Let me point out for an affine map phi t, this term, the first term here, is equivalent to the one that we used when omega is a convex polygon. For the error analysis, again, we have a priori bounds because pi hu is in our constraint set, and we can analyze the error by using the fundamental theorem of calculus, together with techniques for DG methods for elliptic problems in non-divergence form. However, we need to develop several new estimates for functions in the isoparametric finite element space. First of all, we need an inverse estimate. We need a discrete Sobolev inequality and a discrete Miranda-Talenti estimate. Then we have the same error estimate and the energy norm defined on the domain omega h. And we also have estimates in our three lower order norms. And we can use our error estimator to, hold on, wait till it catches up. That is weird. There, finally came. The lag on this is slow. So we can use the error estimator, A to H, to monitor the convergence of the approximate solution. So now let me show you the numerical results for two examples on an elliptical domain. In the first example, we have a smooth exact solution. And we compute the relative errors and the error estimator for an approximate solution UH tilde. These are our results. In less than 7 seconds, we have computed a good approximate solution. And we observe the reliability of our error estimator. And we also observe second order convergence for the error in the H norm and also for the error estimator. In our second example, the exact solution is unknown. So we'll use the error estimator to monitor the convergence of the approximate solution and also to check the value of the cost. These are our results. We see that both the error estimator and the cost are going down to 0, which confirms the convergence of the approximate solution. and we can compute a good approximate solution in about 15 seconds. So let me end with some concluding remarks. So using nonlinear least squares methods to solve finite dimensional nonlinear equations is a classical approach. We've adopted this idea to tackle the Monge-Ampere equation. So these are the ingredients of our approach. First of all, we design novel finite elements that can enforce the element-wise convexity of the discrete solutions as box constraints. We formulate discrete constrained nonlinear least squares problems with regularization and penalty terms that lead to a priori bounds. We solve the discrete problems by globally convergent optimization algorithms that will terminate near stationary points of the cost function with an arbitrary initial guess. We derive error estimates by using the fundamental theorem of calculus in order to reduce the error analysis to a linear elliptic problem. And we construct an a posteriori error estimator that can monitor the convergence of our computed solutions. We can also design nonlinear least squares methods for other problems, such as the Pucci equation that has no convexity constraint. So we've already completed this. Details can be found in these two papers. We can also consider the Minkowski problem, where the key idea is to find the support function. We can compute the support function of sigma by applying the nonlinear least squares approach to the 6 simple Monge-Ampere equations on the 6 faces of our cube, with the Dirichlet boundary conditions replaced by appropriate compatibility conditions on their common boundaries. One of our current projects is on the prescribed Gaussian curvature problem that I also mentioned at the beginning of the talk. So here, if phi is a strictly convex smooth function on the closure of omega, so that phi is 0 on the boundary, and k is smooth positive function on omega closure that satisfies this compatibility condition, then the Dirichlet boundary value problem has a unique, strictly convex smooth solution. The convexity of the approximate solution can be enforced by our exotic enhanced cubic Lagrange elements. The challenge is that the linearized equation has a convective term, so that the Cordis condition is not satisfied in general. And we cannot use the stability estimate for elliptic equations in non-divergence form. But we can include additional penalization to turn it into an elliptic problem in divergence form with a convective term. And then we can use the classical stability estimate for such problems. The optimal transport problem between 2 strictly convex smooth domains, omega and omega star, can also be reformulated as a non-standard boundary value problem. So this problem has a strictly convex smooth solution unique up to an additive constant. We can rewrite this boundary value problem in this form, where the boundary of omega star is given by rho equals 0. This linearized problem is an elliptic problem in non-divergence form with a convective term and an oblique derivative boundary condition. In the special case where phi star is a constant, the convective term is absent and the stability of the linearized problem for DG methods has already been investigated. In the general case, we can use additional penalization to turn a linearized problem into an elliptic problem in divergence form, and then we can use the classical stability theory for oblique derivative boundary value problems. This is the two Hessian equation in 3D. This problem has a unique solution, smooth solution U, so the Laplacian of U is greater than or equal to 0 on the closure of omega under these three assumptions. First of all, our domain is strictly convex. Psi and phi are smooth functions, and psi is strictly positive on the closure of omega. So let me point out that the two Hessian equation is a generalization of the Monge-Ampere equation because in 2D, sigma 2m is the same as the determinant of m. The linearized operator is uniformly elliptic if psi is strictly positive and the Laplacian of U is greater than or equal to 0. We can use exotic degrees of freedom to enforce the non-negativity of the Laplacian. In 3D, uniform ellipticity does not imply the Cordes condition. But we can overcome this by including additional penalization to turn our linear problem into an elliptic problem in divergence form. Another challenge is to extend the 2D isoparametric map to 3D. Now, the two Hessian equation appears in the prescribed scalar curvature problem, just as the Monge-Ampere equation appears in the prescribed Gaussian curvature problem. Finally, we have a Monge-Ampere equation in 3D. The linearized operator is uniformly elliptic if and only if psi is strictly positive. The two Hessian and the Laplacian of U are greater than or equal to 0. We know how to enforce the linear constraint for the Laplacian. The challenge is to enforce the quadratic constraint for this two Hessian. So let me end with an interesting fact. The city of Paris recognizes scientists in some of its street names. So many of my trips have been based in the Fifth area, the center of Paris, where Rue Monge is located. Many of you, if you've been to Paris, you probably walked on Rue Monge at some point. But I took an excursion further out to the 17th a little while ago so that I would have this nice pair of street signs. So thank you for your attention.
So is there any questions?
Thank you for a very interesting talk. I have two curious questions. The first one is about the regularity you impose on the solution. EH4 too stringent, or we can relax a little bit? That's the first question. The second question is also related to that, is how to solve the Monge-Ampere equation on a triangle with the right-hand side number 1 and the boundary is 0, because that's a very simple problem. It turns out that the solution is not H1, that because there's an explicit solution, and the solution turns out to be not in H1. Thank you.
Okay, well, these are the regularity requirements we needed for our theory. Right, we haven't explored relaxing anything. And we have not done that example you're asking in particular, so it's something we should explore.
So you mentioned at the end you check the convexity of your numerical solution. So during the optimization process, is the convexity enforced through all the time?
There's a numerical check as we do the algorithm. I can show you that we have an appendix in the Numerische Mathematik paper that explains how this is done.
So it is the convexity is
It's
maintained.
It's maintained throughout the company.
Okay, any other question?
For the talk, very basic question. So could you help me understand, is the convexity something you can check, you can prove, or something you assume?
We check it numerically throughout the computation. As I just said, there's a procedure, but I can point you to the paper. It's an appendix to our paper, how
So
it's done.
a priority you assume it and eventually you check it.
We check it as we go through.
I see.
So anyone else? Okay, maybe I have a question. So I noticed that for the arrow in the L2 and H1 norm, you get the same order as the H2 norm and the energy norm you have. So does this mean that you have some suboptimal error rate for this L2 norms or H1 norm? Because for linear problems, for instance, when you prove the L2 norm, you should get higher order, right?
But these are the estimates we can prove.
Yeah.
But in practice,
Yeah. So in practice, you get something better,
we can
right?
get better. We get better in practice. But that's what we can prove right now. That's what we can prove.
Okay, thank you. Okay, if there's no other questions, so let us thank our speaker again. And